and then do the usual share screen. Take me a minute to set that up. Connect your iPhone or iPad. Wait, what? No. What is it saying here? Trust this computer. I think I want to trust it. What? I'm sorry. This is giving me. This is not giving me what I want. Let's see. Screen sharing. Let me stop screen share and try it again. This is what I want. I probably clicked the wrong thing. Let's do this here. All right, this is good. This is taking its time, and I don't know why. Okay, here we go. It says it's unable to connect. Let me try it again. That ought to work. I don't know why this isn't working. Let me do this again. I don't like having technical difficulties when I'm trying to get started on this, because there's no time for it. Let's try it again. Okay. I think it's a little bit too large. Yeah, it seems to be working all right. Yeah, I'm going to get started because there's actually quite a bit of material to review. So we got started in the last lecture on the theory of rotations, mainly operations in ordinary three-dimensional space. And so let me review what we did. So we define a rotation as a map from 3D space into itself, such that it leaves the origin of our coordinates fixed and such that all distances are preserved. So you can write x prime equals rx, where r is the rotation operator and x prime are respectively the old point and the new or rotated point. The rotation matrix is related to the rotation operator by being basically the matrix elements of that operator with respect to the basis. This EI here, E hat I means E hat I 1, 2, 3 means the same thing as x, y, and z, the unit vectors along the coordinate axes. So the rotation matrix is just matrix elements exactly in the same sense as in quantum mechanics of the rotation operator. And if you make that interpretation, the upper equation x prime equals rx can also be interpreted as just matrix multiplication of a matrix times a vector to give you the new vector for the rotated point. The fact that the rotations preserve distance implies that the R transpose, now speaking of the matrix, is the identity, which implies that R inverse is R transpose. And it also implies that R times R transpose, that is to say, in the reverse order of what's over here, is also equal to the identity. These facts in turn imply that the determinant of R is either plus or minus 1. And if the determinant of R is plus 1, we speak of a proper rotation. And if it's minus 1, we have an improper rotation. Now, for this lecture and the next couple of lectures, the next several lectures, we're going to be dealing only with proper rotations. And so mostly everything I write down, it'll be assumed that it's a proper rotation only. Still, let me point out that there's two groups here. There's a group O3 of orthogonal 3x3 real matrices. And then there's a group SO3, which has the additional condition that it be a proper rotation, that is that the determinant is 1. So that's some terminology then and some basic facts about rotations. Now, we also looked at infinitesimal rotations last time, and the story is this. if I write R as identity plus a small correction A, where A is a small matrix, or the matrix of small matrix elements, we find from the definition of rotations that A is an antisymmetric matrix. So this leads us to the subject of antisymmetric matrices, which are important in the theory of rotations. If we have such a matrix, we can parameterize it by three real numbers, lowercase a1, 2, 3, arranging in this form, as you see here in this matrix. This gives us a correspondence in between antisymmetric matrices and real three vectors. And I'll indicate that correspondence by a double-headed arrow like this. You can convert from one to the other, and basically it just stands for this formula. This matrix A can be written in another way too, is by using a set of basis matrices for antisymmetric matrices. I call them J1, J2, and J3. The expansion coefficients are A1, A2, and A3. You can see the A1 appears here with a 1 and -1 in that slot, and that's just where the J1 has its non-zero entries. So these J1, J2, J3 matrices, here I'll bring the J3 out so you can see it better, are the basis matrices for antisymmetric matrices. These J matrices are important, and they have a number of properties I'm summarizing here. One of them is the components of them. Oh, by the way, the parentheses on the J matrix here indicates that labels the matrix and does not represent the components of the matrix. As you can see here, J1 is the entire matrix. But if I want the components of Ji, I can write it this way as Ji sub Jk. And that, in fact, with a minus sign is the Levi-Civita symbol epsilon ijk. That's really just a way of encoding the Levi-Civita symbol. An important property of these J matrices is their commutator. Commutator of Jx with Jy is equal to Jz in cyclic permutations, which is captured by this formula number 2 here. Oh, by the way, this linear combination of the J matrices, we'll write it this way as A vector dotted into J vector, but A has to be understood here that it's a vector of ordinary numbers, whereas J is a quote unquote vector of matrices listed explicitly, as you see down here. So this is like this notation used like A dot sigma in the case of the Pauli matrices, except those are 2 by 2 complex matrices, and the J's here are 3 by 3 real matrices. Except for that, the notation is very similar. So these J matrices satisfy a commutation relation, is that Jx, Jy is Jz and cyclic variations on that. If I dot these J matrices with 2 vectors A and B, then I get antisymmetric matrices A dot J and B dot J. Remember that's what this A is. This is just an expansion of an antisymmetric matrix, this linear combination of the J matrices. So A dot J, B dot J is the commutator of 2 antisymmetric matrices. And that commutator is itself another antisymmetric matrix, and the coefficients are A cross B. So this is just an identity, which is actually trivially equivalent to number 2. That's why I call it number 2 prime. There's another identity here, which I started on proving at the end of the hour last time, that if you take an antisymmetric matrix and write it as A dot J and multiply by a vector U, it gives you the same answer as taking the corresponding 3 vector and forming the cross product with U. So this is an important property that's quite useful for converting cross products into matrix notation, which is oftentimes a useful thing to do. In any case, if I do that, and let's see, what am I doing here with my papers? Here we are. The proof of that property, number 3, is obtained just by writing out A dot J as a full 3 by 3 matrix and writing out vector U with its 3 components and then just multiplying them out. And if you do that, you'll see it's equal to A cross U. And this is straightforward proof of that identity there. You can do it other ways too. All right. Something else we talked about last time is the axis angle parameterization of proper rotations. An axis is just a unit vector, but it represents an axis of a rotation. If I use my hand, you rotate like this with your thumb pointing in the direction of the axis, and the angle is theta. In other words, use a right-hand rule. And this gives us a parameterization of proper rotations, which we write as R of n hat comma theta. And it's a fact which I didn't prove, but one can prove that every proper rotation can be written in axis angle form. It's clear that, I think it's clear geometrically that the axis and angle do specify a proper rotation, but the converse is true also, is that every proper rotation it has an axis and an angle. So there's no loss of generality in writing a proper rotation in axis angle form. All right. Now, given that every rotation has an axis angle form, then the problem arises here, is posed by the material I've given so far, is that suppose we have an infinitesimal rotation, which, to remind you, looks like this. It's identity plus the correction A, which we write as A vector dotted in a J vector, where the components of A are small, or the free vector A is small. This statement is made that every proper rotation can be written in axis and angle form. So the question arises then is, what is the axis and angle of this infinitesimal rotation? And you can answer that by drawing a picture, or at least this is part of the answer. Let's take the axis n hat down here. It's kind of pointing upwards, and we'll extend it as a dotted line going on up. And we want to apply a rotation of a small angle theta much less than 1 to a vector u, which I've drawn sticking out here like this. U is just an arbitrary vector. Now, when you rotate it by a small angle, well, if you rotate it by any angle, you can see what it's going to do. It's going to sweep out a cone. I may use my fingers. It'll sweep out a cone going around the axis, you see. But if the angle theta is very small, then it just sweeps out a small part of the circle of the top of the cone. That's what it is. And a little geometry shows you that that vector delta u, let's call it delta u, is the increment in u under the small rotation, is given by theta n hat crossed u, like so. So this is the beginning of an analysis of small rotations in axis angle form. And with that, I shall switch to a blank piece of paper and carry on with a demonstration. So this means that our infinitesimal rotation acting on u, which I can also write as identity plus a multiplying u, we can write it in two forms. It's u plus delta u, and that's the same thing as u plus theta times n hat crossed u. That comes from just the geometry of looking at that picture I drew on the last page. On the other hand, the I plus AU makes it look, it can be written this way as I plus vector A dotted into vector J of matrices multiplying U. And that's the same thing from the I, which just gives me U, that's the identity times U. And the A dot J times U gives me plus A cross U. And so comparing these two things together, you can read off the relationship between A and the axis and angle. And what you find is the vector A, which appears in this infinitesimal correction matrix, is theta times n hat. Or in other words, to solve it the other way around, theta is given by the magnitude of A like this, and n hat is given by the direction of A. It's A vector divided by its magnitude. So what this tells us then is that an infinitesimal rotation in axis angle form, if I have r of n hat comma theta, and it to be infinitesimal means the angle theta is very small, then this can be written this way as identity plus theta times n hat dotted into our vector of antisymmetric matrices J like that. And let me box that because that's a useful formula. It's a small angled form for a proper rotation written in axis angle form. Okay. Now, we see explicitly the axis and angle here. Now, what do we do if theta is not small? Suppose theta is not small. You may remember we did some things with translations, and we sort of bootstrapped ourselves up from a small translation, an infinitesimal translation, to one of finite displacement. And I did it in two different ways. One was to solve a differential equation, and the other one was to multiply together a large number of small displacements. And likewise, where I'm going in the next couple of steps, one can do it either of those two ways. I'll do it by a differential equation, just to pick a way of doing it. Let's suppose theta is not small, and we're looking at the rotation by an angle, axis n hat at an angle theta. Let's take the derivative of this with respect to theta and work out a differential equation that we can solve. We'll do this by using the definition of the derivative. So dd theta of this thing is equal to r of n hat comma theta plus epsilon minus r of n hat comma theta divided by epsilon. It's the definition of a derivative. Now there's something I forgot to mention earlier, so I'll write it up here, which is that in axis angle form, if you multiply two rotations that, let's say theta 1 and r of n hat comma theta 2. Can you read this? The idea is they have the same axis n hat, the different angles theta 1 and theta 2. This is just given by r of n hat comma theta 1 plus theta 2. In other words, rotations about a fixed axis commute with one another because theta 1 plus theta 2 can be written in either order. And the angles in questions just add. And I think that's obvious if you just think about the n hat and theta, the rotations about the axis. If you do it twice, just compose the rotations one on top of the other, the angles just add. Now that only works if the axes, the two axes of the two rotations you're multiplying together are the same. If you multiply rotations that have different axes, then it's much more complicated. And in fact, they don't commute with each other anymore. The rotations in general don't commute. This is just a special case. If the axis is fixed, then they do commute. All right. So that means this r of n hat comma theta plus epsilon can be written in the following way as r of n hat comma epsilon times r of n hat comma theta. Okay, like so. Let me draw a line here to separate off what I'm doing. That first factor can be written that way. And thus both terms in this numerator here now have a factor of r n hat comma theta on the right and can be factored out. So this can be written this way as the limit as epsilon goes to 0 of r of n hat comma epsilon minus the identity divided by epsilon, that whole thing multiplied on the right by r of n hat comma theta, like so. Let me write it like that. On the other hand, since epsilon is a small angle, we can use a small angle form up here, except we'll replace the theta by the epsilon. So if we do this, you can see the identity will cancel, the epsilon will cancel, and this leading factor just turns into n hat dotted into script j. That's multiplied by the remaining factor r of n hat comma theta. And so in this way, we obtain a differential equation. The derivative of r of n hat comma theta with respect to the angle theta is n hat dot j times r of n hat comma theta. This has the initial conditions that when theta is equal to 0, we have, of course, the identity matrix because 0 angle of rotation means the identity. So this is a simple differential equation and is easy to solve. And we end up finding that r of n hat comma theta now, when theta is not necessarily small, is equal to e to the theta of n hat dotted into script j. In other words, we get to write it as an exponential of really it's an antisymmetric matrix, you see. It's an exponential of an antisymmetric matrix. So this is for any theta here, like this. And it generalizes what we had above, which applied to small theta. You can see that if you expand out this exponential series, you get the first two terms are in fact exactly the small angle formula up above. But if you feel like going to higher order, you can now do so. You have 1/2 theta squared, the matrix n hat that j squared, and so on like this, and you can carry out the Taylor series going out to as high as you want, however high a power you want to go to. So these two things that I've kind of boxed here are important results. We use them quite a few times in the following lectures tonight and in later lectures. The infinitesimal version of a rotation, in which the correction matrix is explicitly represented as a linear combination of these bases of basis matrices of antisymmetric matrices. And then we have a corresponding exponential version, which applies for any angle theta. These matrices that are getting exponentiated here, you get the successive powers of n hat dot j over and over again. Here's the square and the cube will be in the next term and so on. It's possible to use the properties of those j matrices to work out those higher order powers of n hat dot j and to re-express them back in terms of lower powers. This is something that you did on your first homework exercise involving the Pauli matrices. So I hope you remember the general plan of doing that. I'm not going to go through the details of it, but I'll quote the results. And it can be summarized this way, is that r of n hat comma theta, if I allow it to act on an arbitrary vector, let me call it u, can be written this way. It becomes the cosine of theta times u plus the factor 1 minus cosine theta times n hat dotted into u plus the sine of theta multiplying n hat crossed u. let me box that because this is an explicit formula for what a rotation, proper rotation in axis angle form does to an arbitrary vector. And I may come back to this later on at a later point in tonight's lecture. This formula, by the way, is fairly easy to understand if you just draw a picture of an axis and a vector that gets rotated by a finite angle. What happens is that the component of the vector parallel to the axis doesn't change. That's this n hat dot u here times n hat. That's the component parallel. Whereas the components that are perpendicular are rotating in a plane, in a two-dimensional plane that's orthogonal to the axis. And there it's just like a 2x2 rotation with sines and cosines in it. And that's what you see here with these sines and cosines. So that's another way of deriving this formula, but you can also get it by summing the exponential series, and you end up creating the Taylor series for sine and cosine and theta appear in there. All right. Anyway, so this is now the exponential version of a rotation in axis angle form. Now, the next topic I'd like to address is based on a certain identity, and I'm going to write down the identity first and then show you how it gets used. Let's suppose I have two vectors A and B and I form their cross product, A cross B, like this, and then I rotate the result. This is a proper rotation now. It turns out the answer is the same if I rotate the vectors first and then take the cross product. In other words, you can say it this way, is that it doesn't matter whether you rotate first and take the cross product or take the cross product and then rotate, the answers are the same. This formula is sometimes expressed in words by saying that the cross product transforms as a vector. It only works, by the way, if this is a proper rotation. I want to emphasize that here, because if you go through the proof of this, and in fact, I'm going to ask you to do that on a homework exercise to derive this formula, you'll find that it relies critically on the fact that the determinant of R is equal to +1. But in any case, this is a useful formula. All right, now then, I want to use this formula to derive some. So I'm not going to prove this formula. As I say, I'm going to leave it for an exercise for you, but I want to derive some important results that follow from it. In the first place, allow me to translate these cross products into this vector notation. Let's see if into this matrix notation. Let me see if I can find the place where I presented that material. Yes, here it is. Here is the identity. It's A dot J, which is an antisymmetric matrix, multiplying U is the same thing as A crossed U. And the proof is given by just multiplying it out, if you'll recall. So let's use that result here. So the this A cross B can be written so the left-hand side, the R I'll just copy. As far as the A cross B is concerned, I can write it this way as A dotted into J vector. Remember that that's now an antisymmetric matrix multiplying B. So on the left-hand side, what I've got is a product of two matrices. It's the same as the left-hand side up above. On the right-hand side, I take the vector RA, rotated vector RA, I dot that into J. That gives me an antisymmetric matrix. And when I multiply it by something that's equivalent to the cross product, so that's the right-hand side is this then. It's RA dot J, that matrix times RB. Okay, this is just a transcription of the identity above. Now, what we've got is two matrices multiplying B on the left and the right-hand side, and they're equal to each other. And B is arbitrary. So that means we can cancel the B's. This really becomes a matrix identity. And we can rearrange this slightly by multiplying through by R transpose from the right, which will clear the R there. And if we do this, we end up with a useful identity, which looks like this. It's R times A dotted into J times R transpose is equal to RA dotted into J. Okay, let me box that because this is a useful formula, which appears in various places. I give it a name, I call it an adjoint formula. We will use a variety of adjoint formulas quite a bit in this course. Let me go back to an earlier page that I had back when I was doing a summary here and make a comment about the adjoint formula. I pointed out earlier that we get this mapping between antisymmetric matrices and three vectors. And the mapping is obtained just by writing the matrix in this form. What this formula shows you is that if you take such an antisymmetric matrix and you conjugate it by a rotation, well, the first thing to notice is that if you take an antisymmetric matrix and conjugate by rotation, let me write it as capital A instead of A dotted into J, but they're the same thing, RAR transpose. If I form the transpose of that, you run it backwards and take the transpose of all the elements. So R transpose is R. The AA transpose is minus A because it was antisymmetric, and you get R transpose again. So what this shows you is that if you conjugate an antisymmetric matrix by a proper rotation, the result is still antisymmetric. So therefore, it's got to be equal to the linear combination of the J matrices with some coefficients. As I say, of course, the conjugated matrix corresponds to some vector. What's the relation of this new vector to the old one? And his formula says it's just the rotated version of it. So if I could draw this in this diagram here, if I've got A corresponding to 3 vector lowercase a, and I carry out a conjugation here to turn this into RAR transpose, what happens to the corresponding vector is it just gets rotated like this. And when you do that, these two then correspond by the correspondence. All right, so that's just an interpretation of this formula here, which otherwise is a statement, makes a statement that the cross product transforms as a vector. All right, so this is this adjoint formula. We'll use it quite a bit. I want to make an application of the adjoint formula right away, or transform it into another useful form. Allow me to first to begin this. Allow me to first change the notation. Let's take R and replace it by R naught because I want to distinguish it from other R's that will appear later. And let's take the vector A, and replace it by theta times n hat for some axis and angle, which of course will be an axis and angle of a rotation. If I do that, then the formula up above now looks like this. It becomes R naught times theta n hat dotted into J vector. I'll put parentheses around that. R naught transpose is equal to, on the right hand side, it becomes R acting on theta n hat like this, dotted into J like that. Okay. Now that just by change of notation. Now allow me to exponentiate both sides, like so, to e to those matrices. On the left-hand side, you can bring the R naught and R naught transpose down out of the exponent. And I'll explain that. But anyway, that's what you can do to the left-hand side. Now let me make a digression as to why you can do that. If I have a matrix, if X is a matrix and I compute e to the X, it's just a Taylor series. So it looks like this. All right. Now let's suppose I conjugate this with a matrix. I need a name for it. I'll call it, well, we're conjugating R's. Let me call it an R here. So R e to the X, R transpose, let's say. What is that equal to? Well, it's equal to R times this Taylor series R transpose. And RR transpose in the identity just gives me identity. On the X, it gives me R X R transpose. Then we have the 1/2 X squared term. Let me write this as R. And instead of writing as X squared, I'm going to write it as X times R transpose times R times X. And then I have the R transpose on the right, plus dot, dot, dot. And that you can see as identity plus RX R transpose plus 1/2 of RX R transpose squared plus dot, dot, dot. And that becomes equal to e to the power of RX R transpose. And so these two things are the same. And this just shows that you can bring the RR transpose up into the exponent, you see. All right. In any case, that explains what I did with the left-hand side here. As far as the right-hand side is concerned, well, let me continue the left-hand side a bit. The left-hand side, the matrix in the middle is now a rotation in axis angle form. It's R naught times R of n hat comma theta, as you can see, and then R naught transpose. And on the right-hand side, this is also a matrix. This is also a matrix in axis angle form. That should have been an R naught there, except the axis is not in hat. It's a rotated axis, R naught in hat. So I'll write it this way. It's an R of R naught in hat, comma theta. And let me box that because this is another important formula, which is really just an exponentiated version of the adjoint formula. So I'll call it that, call it the exponentiated version of the adjoint formula. But notice what it says. If we take a rotation in axis angle form and we conjugate by a different rotation, let's say it's like a fixed rotation, we get a new rotation in which the axis has been rotated by that R naught and the angle hasn't changed. So this is sometimes stated in words by saying that the axis of a rotation transforms like a vector because it gets rotated when you conjugate the rotation. And the angle of a rotation is a scalar. It's invariant. It's invariant under this transformation. This is one way of saying this. All right. So anyway, these are useful formulas. Now, are there any questions about this so far? All right, this is just developing the formalism of three-dimensional rotations. The next topic I'd like to address is that of Euler angles, which I'm sure you've encountered before. I'll try to make them as painless as possible. The idea of Euler angles, in the first place, we have already a parameterization of rotations. It's the axis angle parameterization I've been talking about quite a bit, and it's very useful for all kinds of purposes. But there's another parameterization, which is the Euler angles. And so now I want to tell you about that one. The idea of Euler angles I can explain by first of all, drawing some axes, X, Y, and Z like this. And if we take the unit vectors along these axes to be E hat sub I, where I runs from 1, 2, and 3 like that, we can define primed unit vectors by applying a rotation to them. So the primed axes are just the rotated versions of the unprimed axes. Suppose we do that. And maybe the X prime axis ends up sticking out like this, and the Y prime axis comes down like this, and the Z prime axis comes out like that. You end up getting a picture that's a little bit hard to follow with your eyes, but you get the general idea. There's a new set of axes there. Now I'm going to make the geometrical claim, which I claim is geometrically obvious, which is that if you specify the orientation of all three of the primed axes, that uniquely defines the rotation that map the old axes into the new ones. And so we can obtain a parameterization of the rotation if we just parameterize the directions of the three primed axes. So let's do that. Let's start with the Z prime axis. I'm going to draw the picture again with X, Y, and Z, the original set of axes like this. But I'm only going to draw the final Z prime axis. Allow me just to do that one and leave off X prime and Y prime for now. So we want to specify the direction of Z prime. We're going to need to do the X prime and Y prime also, but let's start with the Z prime. Well, one way to do that is just to introduce the usual spherical coordinates for the direction of Z prime. There's a polar angle and there's an azimuthal angle. Let's call the polar angle alpha and the azimuthal angle beta like that. Okay. I'm not going to call them theta and phi, but that's basically what they are. They're the theta and phi of Z prime, the Z prime axis. All right. Now then, it's possible to write down a rotation that maps the Z axis into the Z prime axis. If we have some rotation R up here that we're thinking of, that it has a specified action in all three axes, Z prime, X prime, and Y prime. But let's just look at Z prime for now. Allow me to define a rotation I'll call R naught. And it works like this. It is first of all a rotation about the y-axis by the angle beta, followed by a rotation about the z-axis by an angle alpha. You know, you have to put it in this order because the one on the right is the one that's applied first, and the one on the left is applied second. Well, this R0 has the property R naught that if I apply it to the z hat axis, I get the z hat prime axis. In other words, R naught moves z into z hat prime in this picture here. You can see it in the following way. If I go back to the original axes, X, Y, and Z like this, and I first apply the y-axis by angle beta, here's your angle beta about the y-axis using the right-hand rule. it'll take the z-axis and it'll rotate it in the xz plane like this down by an angle beta. You can see that geometrically. If I then follow it by rotation about the z-axis by an angle alpha, here's the z-axis rotated by alpha, then this vector sweeps out in a cone like this and goes over here to its final position, as I've drawn it up here, and it becomes the z prime axis. So by drawing a picture like this, you can see that this equation is true when R naught is defined in this way. So R naught is a rotation that puts the z prime axis into the desired final position. There's no reason to expect that it does the same for the x prime and y prime axes. In other words, R naught acting on x prime equals, on x equals x prime is probably wrong. And probably the same thing is true for the y-axis. That one is wrong too.
Sorry, I just have a question.
Yes, go ahead.
I'm having a hard time seeing why alpha and beta are not switched. It seems like beta is the distance from the z-axis.
Well, thank you so much. You have such eagle eyes, because I got them backwards in this picture. This should be a beta and that one should be an alpha. And let me just say that in the future, if you are suspicious that something like this is not right, interrupt me right away, because I might go on all night with making mistakes. No, you're quite right. Beta is the polar angle and alpha is the azimuthal angle. Thank you very much for pointing that out. I think these other pictures are right though, and this is correct. Okay, I hope that wasn't too confusing. All right, so as I was saying, this R naught defined in this way does not put the x prime and y prime axes in the right orientations. However, the orientations of the x prime and y prime axes can only be wrong by a rotation about the z prime axis. That is to say, the rotation R naught is a rotation, so it preserves orthonormality. So the x prime and y prime axes are mapped by R naught into axes which are in the plane perpendicular to z prime. Well, that's the correct plane for the final x prime and y prime, and so they can only be wrong by a rotation in that plane. And therefore, what we can say is that the rotation R, which we're trying to represent up here, can be represented in the following manner: is we have our R naught initially, we apply that, and then we follow it by a rotation about axis z hat prime by an angle gamma. Gamma is a new angle that fixes this up in the xy plane. So this then becomes R of z hat prime comma gamma times R of z hat comma alpha times R of y hat comma beta. All right. And the claim is that, and I think it's very clear on the basis of the geometry, that there exist angles alpha, beta, and gamma such that an arbitrary proper rotation can be written in this form. Now, this is a product of rotations about coordinate axes, two of which are the old axes and one of which is a new axis. And it's not very convenient in practice for that. We'd like to have rotations about either just the old axes or just the new ones. Let's make it just the old ones. We can do this in the following way by introducing an R0 transpose at the beginning of this. And then we got the R of z hat prime comma gamma in the middle, and then we have the R0 at the end, like this. So I just inserted R0 transpose right here before this factor. But now what we've got is a conjugation of a rotation. And so by our previous formula, this is equal to R0, we copy this R0, the first factor here, we copy it. And as far as the rest of them, this becomes R, the rotation, about the inverse rotated by R naught inverse z hat prime comma gamma. However, R naught inverse z hat prime from this formula here is just equal to the original axis z hat. So this becomes R of z hat comma alpha times R of y hat comma beta times R of z hat comma gamma. And we have alpha, beta, gamma angles, z hat, y hat, z hat axes, and we've got a factorization of an arbitrary rotation in this manner. And let me box that because this is the Euler angle representation of the rotation. It basically amounts to factoring an arbitrary rotation into products of rotations about the coordinate axes. In this case, the sequence is z, y, z. Okay. There are lots of ways of creating Euler angles, and this is only one. This is what would be called the ZYZ convention. You can see why. If you study classical mechanics and rigid bodies, which I'm sure you've done by this point in your career, you probably use the ZXZ convention, which is popular in books on classical mechanics. In quantum mechanics, people prefer the ZYZ convention, which was promoted by Wigner for reasons which I'll explain later on. It's more convenient. But there's other possibilities as well. If you become an airplane pilot, you learn about pitch, yaw, and roll, and that's an XYZ convention for Euler angles. In the case of pitch, the axis is runs along the wings of the plane. In the case of yaw, the axis is the vertical axis, so you start flying the plane sideways, sort of. And in the case of roll, the axis is the fuselage of the plane itself, so that's what you do when you want to go into a bank. Anyway, these are different conventions for Euler angles. The angles in question are the range on the angles is pretty easy to see because remember that the alpha and the beta, in fact, this is worthwhile remembering, the alpha and beta are just the usual spherical angles of the z hat prime axis. So the range on alpha is the usual one for what usually we'd call alpha, the phi angle. Alpha ranges from 0 to 2 pi. The beta goes from 0 to pi, less than or equal to cover the South Pole. And as far as gamma is concerned, in general, we need a range of 2 pi in order to correct what's wrong in the x prime, y prime plane. So gamma goes from 0 to 2 pi like this. Anyway, so these are the ranges on the Euler angles. And inside the interior of these ranges, there's a one-to-one correspondence between proper rotations and rotations. All right. So this is a second parameterization in addition to the axis angle parameterization for proper rotations. All right, I think that's all I want to say about Euler angles. Are there any questions about that? All right. The next thing I want to talk about is the commutation relations of rotations. As I mentioned earlier, rotations whose axes are not equal to each other, don't have the same axis, don't commute. So in general, rotations don't commute. In general, R1, R2 is not equal to R2, R1. In quantum mechanics, we oftentimes use the ordinary commutator to measure the extent to which operators don't commute. There's something that's used here too, and it's also called a commutator, but it's a different definition. This is what you find in a math book if you look up the word commutator. Commutator, call it C, of two rotations, R1 and R2, is defined this way. It's R1 times R2 times R1 inverse times R2 inverse. I'll show you in a minute that this commutator is actually related to the commutator that you're used to in quantum mechanics. But in any case, this is for now is what we'll call the commutator of two rotations. This is more useful than the usual commutator. You could, of course, compute this if you want R1 comma R2 as a commutator, but this is not a rotation, you see, and so it takes you outside the space of rotation, so we don't do that. The C actually is a rotation, as you can see. Something else you can see is that if R1 commutes with R2, then I could rearrange the factors and then the rotations and their inverses cancel each other out and C becomes the identity. So C is equal to the identity for rotations that commute, and otherwise it's not. Now, what I'd like to do is to examine the commutator by this definition in the case of infinitesimal rotations. First, let's just talk about rotations in axis angled form. Let's say R1 is equal to R of n hat 1 comma theta 1, like this. Actually, before I do that, let me make a digression about axis angle notation. Let's just make it R of n hat comma theta. This, as I explained earlier, is equal to e to the theta times n hat dotted into script j, like so. And you may notice from this formula that the answer depends only on the product of the angle times the axis. And so for this reason, we sometimes define a vector of angles as n hat times theta. So the vector of angles theta vector is a vector whose magnitude is equal to the angle of the rotation and whose direction is equal to the axis of the rotation. And if we do this, we can write this rotation as e to the theta vector dotted into j. And by obvious notation, we can also just write this as r of theta vector. It means the same thing, really. All these just different notations. Now let's do this for R1 and R2. let's do these similarly. So R1 is equal to, let's write it as R of theta vector 1, and R2 is R of theta vector 2, like so. Oh, by the way, we can also make another notation here. We can write, let's say A1 is equal to theta 1 vector dotted into J, and A2 is equal to theta 2 vector dotted into J. These are antisymmetric matrices. And if so, this R of theta 1 is the same thing as e to the A1, and this is equal to e to the A2. So, okay, now this is R2 here. Now, let's return to this commutator so defined up here, and let's examine its behavior when the rotations are infinitesimal. I'll tell you what, let me make yet another digression that'll motivate this a little better. You know, if you're designing a spacecraft or something, and you want to a spacecraft, and you want to be able to orient the spacecraft in certain directions, as you must do, for example, with the space telescope. One of the ways of doing it is to just simply have a motor inside the spacecraft with a flywheel on it. It doesn't have to be a big flywheel, and you turn the motor on, and the flywheel starts spinning. And what happens is, by conservation of angular momentum, is the rest of the spacecraft rotates in the opposite direction in order to conserve the total angular momentum. When you want to stop the spacecraft rotating, you just turn off the motor and stop the flywheel. Now, if the flywheel has a small moment of inertia and the spacecraft has a large one, it means you can make fine adjustments by just running the motor for a short period of time. Now, of course, this only causes the spacecraft to rotate about a single axis, of course. So if you want to generate other rotations around different axes, you might want to have another motor in a different direction, like this, like maybe the X direction and the Y direction, something like that. Or maybe you think you might need the Z direction as well. Do we need these little motors in 3 different directions in order to control the orientation of the spacecraft? Well, now it becomes a theoretical question, not a practical one, because practically you might even want to have more than 3 motors. But as a theoretical question, in fact, you only need 2, because if you're able to rotate the spacecraft around the X-axis and you're able to rotate it around the Y-axis, then by composing the 2 of them, you can generate rotations about the Z-axis. It turns out that you rotate around X a certain amount, and then rotate around Y a certain amount, and then unrotate around X that same amount, and unrotate around Y the same amount. It's kind of like taking going along a path. A square path in rotation space is kind of the idea. When you come back to where you started from, you don't have the identity, it turns out, rotation, but rather you have rotation about the Z-axis. And you can see the mathematician's definition of a commutator is appearing here in this description. So this physical picture, I hope, explains, or at least motivates, why this is an interesting object to look at. Anyway, let's look at this now. And let's suppose that these 2 rotations, R1 and R2, are small angle rotations, near identity rotations. Then clearly C itself is a near identity rotation, product of 4 near identity ones. And the question is going to be then, what is the axis and angle of C in terms of the axis and angle of R1 and R2? It turns out, to answer that question, you have to carry the Taylor series for R1 and R2 out to 2nd order. It won't do just to do it to 1st order. I've summarized here on this page kind of the algebra that's involved. Is that here's C, it's e to these A's are these antisymmetric matrices, e to the A1, e to the A2, e to the minus A1, e to the minus A2. And if I just write these series out and carry it out, I want to multiply all 4 of these series together like this, and I've carried them out to 2nd order. You can go on if you want. When you multiply this out, of course, at lowest order, what you get is the identity. And the 1st order correction is just the sum of these 4 terms, but they add up to 0. So at 1st order, you do return to the identity. And when you compute the 2nd order corrections and you multiply them out, there's something like 6 terms. I'll leave it as the algebra to you. When you do it, what you find is, interestingly enough, you get the commutator in the ordinary sense in quantum mechanics of the antisymmetric matrices A1 and A2, and then there's plus higher order terms like this. All right. So if these A1 and A2 are small, I think earlier I was saying let's let A1 correspond to vectors theta1 and theta2. They would correspond also to axes, which you can call n hat 1 to theta1 angle, and theta2 is the same, an axis n hat 2 and angle theta2, like so, where the angles theta1 and theta2 are small. So if the A's are small, then the commutator of the A is small, and C is also a near identity rotation. So let's write C in this form as C of a vector of angles I'll call phi like this, or if I write phi vector is equal to a new unit vector m hat times an angle phi. This is the same thing as C, excuse me, this is the same thing of R of m hat comma phi. We write it that way. And the question is, what's the relation between the phi and the thetas that appeared in here? Well, the answer is this, is that since phi is small, this is the same thing as identity plus phi dotted into J. That's from expanding out the C, the near identity version of the C. On the other hand, the right-hand side here is I plus the commutator of A1 with A2. So that's the commutator of theta1 dotted into script J, comma theta2 dotted into script J. This should be a script J here also. All right. But somewhere on an earlier transparency, except they aren't transparencies, they're pieces of paper, I mentioned that the commutation relations of these J matrices as an alternative form that A dot J commutator B dot J is A cross B dot J. It's really equivalent to 2 here. 2 and 2 prime are really equivalent properties. So now we get to use the commutators of the J matrices, and this turns into I plus theta1 cross theta2 dotted into script J. And so now comparing these two expressions, which have to be the same, you can see that the phi vector is equal to the cross product of the theta vectors. Or if I put it into axis and angle form, it means that m hat times phi angle phi is equal to theta1, theta2 angles times n hat 1 crossed n hat 2. Whichever way you want to describe the relation here, it shows you that the near identity mathematician's version of a commutator has an axis which is in the direction of the cross product of the axes of the two rotations that you are multiplying together. All right. So in particular, x hat, y hat rotations give you, composing them in the manner shown here, gives you a rotation about the z-axis. Okay, so I went through this because this is something we're going to use in the future. And so let me just post this now as a result, which we'll come back to a little later. Are there any questions before I go on? All right. If not, then we move on to the next topic, which is, this finishes what I want to say about rotations in ordinary three-dimensional space. Sometimes I call them classical rotations, except what really is just the geometry of 3D space, Euclidean space. That's really all it is. But these are the kinds of rotations you use in applications to classical mechanics. Let's turn now to rotations in quantum mechanics. Let's suppose we have a quantum system. There's some Hilbert space, which I'll call E like this, and we have states psi that belong to the Hilbert space, things like that. Let's also suppose I've got R, which is a proper rotation. That's to say it's an element of SO3. There's a proper rotation. And I'd like to give meaning to the notion of rotating our quantum system. That's to say we have our quantum system, let's say for simplicity, let's say it's in a pure state psi. We'd like to map it into a new state, which I'll call psi prime, and corresponding to rotating the system. By the way, there's a question of what we mean by rotating a quantum system. You mustn't think that you can take a wave function and somehow go in and, with your hand and twist it around, because the wave function does not represent the properties of a single system. In other words, this is quote unquote, the wave function of the electron does not describe a single electron. It describes an ensemble of identically prepared systems with an electron in them. So one of the possibilities for defining a rotation operator is to rotate the preparation apparatus, the apparatus that prepared the system. And if you do that, then you can say that the systems that are prepared by the rotated apparatus are the rotated systems. This is one point of view. Another point of view is that there are is that time evolution in quantum mechanics sometimes gives rise to rotations. You can well imagine that molecules do that. Molecules are small molecules, and many of them are roughly rigid bodies. And a classical rigid body evolves by means of a time-dependent rotation. And we expect something like that to happen also with nuclei. Same thing there with nuclei as well. So in any case, there are rotations are meaningful and common, in fact, in quantum applications. So we want to say, how does this come about, this rotation? And we are basically going to postulate, but it fits into all the applications properly, that the rotated state, which I'm calling psi prime, is given by a linear operator, which I'll call u, acting on the old unrotated state psi. This linear operator u has to be parameterized by the classical rotation, so I'll put that in there like this and call it u of r. There's different rotation operators for different rotations. So a problem that we face now is to find out what these rotation operators are. What is u of r in terms of the classical rotation r? This is a problem we're going to solve. Won't finish it. Well, I don't know. We might finish it tonight. Some of it anyway. All right. Now, you can well imagine that the answer to this question, what are the rotation operators u of r, depends on the system. It makes a difference whether it's a spin system or a system of a single spinless particle in 3D, or a multi-particle system, or whether it's relativistic or not, or and so on and so on and so on. And that's all certainly true. Nevertheless, there are certain universal properties of these rotation operators that apply to all systems, because they derive ultimately from merely the properties of rotations in three-dimensional space and nothing else. And so we're going to concentrate initially on the properties that are universal to all rotation operators. And then once we've done that and we understand those properties, we'll then turn to specific systems, starting with spin systems, and see how rotation operators are developed for those, including all the physics of those, the idiosyncratic particular physics of those particular systems. All right. So that's the plan. All right. Now then, we're going to proceed this way. The rotation operator R can be written in axis angle form, as I keep saying. And sometimes it's convenient to write this in terms of the vector of angles. And I'll remind you the vector of angles is just equal to the scalar angle times the axis in hat. That's all it is. And this, of course, is equal to e to the theta in hat dotted into j, putting in an exponential form, and so on. There's various relations like this. Now, if I form the u operator, oh, excuse me a second. Let me put 3 dots here because I want to come back to this. I wanted to say something else before I get into this. To go back a few steps, we're postulating that the rotated state is given by a linear operator acting on the original state, and that the linear operator is parameterized by the classical rotation. Let's put some requirements or postulates which this operator needs to satisfy. The first one is fairly obvious, is that u of the identity should be equal to the identity operator. The second one says that u of an inverse matrix should be equal to the inverse of the u matrix. The third one says that u of R1 times u of R2 should be equal to u of R1, R2. So if I apply 2 classical rotations to get R1, R2, the operator that carries that out on the quantum system should be the product of the rotations that did the individual rotations. And the final property is that the u of R inverse should be equal to u of R dagger, which is just a way of saying that these u operators are unitary. We usually require operators that implement symmetry operations such as this to be unitary in order to preserve probabilities. It's usually a fundamental requirement. You want the total probability of finding a particle somewhere in space to be equal to 1, both before you rotate the system and after you rotate the system. So this is ultimately the reason for the requirement of unitarity. All right. Now, so these are the main postulates that we're going to impose on these operators U. And the goal before us is to determine exactly how U depends on R, get explicit formulas for that in different cases. So as I started to say a minute ago, we'll develop some notation first. The R we can write in axis angle form in various ways here. As far as the U is concerned, it's a function of R. So if we write R in axis angle form, U of R of n hat comma theta, let's just define this as U of n hat comma theta. That is to say, let's just label the U operator by the same axis and angle as the classical rotation that it's associated with. Likewise, we can also write this as U of theta vector, I think in a fairly obvious notation. Let's just do that. Now then, with that notation out of the way, the key to solving for these functions U of R, see, we have a function here because we've got a mapping. We have a map that takes us from a classical rotation and maps us into the corresponding operator, unitary operator U of R. And the question is, what is this map? That's what we need to work out. This is U as a function of R. We need to find that function. The key to finding this function is to work initially with the infinitesimal rotations. So let's do that. Let's make the angle small and see what we get. Well, in the case of R of theta vector, we know what that is. That's equal to the identity plus theta vector dotted into our J vector here. This applies when theta vector is small, which is what we're going to assume now. As far as the U is concerned, U of theta vector, what does that look like when theta is small? Well, we can work that out by using a Taylor series. It's given by U of 0. We don't know what U is, but we can expand it in a Taylor series. As U of 0, correction term is the sum I of theta I times partial of U with respect to theta I evaluated at 0 plus dot, dot, dot. Okay. Now, U of 0 by our first postulate here is equal to the identity. So we know that term, but now we've got this first correction term. Now, if you remember what we did with translations operators, the next step is going to be familiar. This is say, I'm going to make a definition. I'm going to define an operator I call J. It's really a vector of operators I'll call J. This is now a capital Roman J, not these script J's I've been writing like up here. These are to be distinguished now. This is J as a vector of operators. It's defined in this way as equal to, let's see, I want to make sure I get it right, is equal to IH bar times the partial of U with respect, or let me write this way, as J sub I, the ith component of J, is IH bar partial of U with respect to theta I evaluated at 0. Put a box around that. That's a definition. It's just a way of defining these operators, the derivative operators here. But I want to point out that although the U depended on theta, so there's a huge number of U operators, these derivatives are evaluated at 0. So there's actually only 3 operators corresponding to I equals 1, 2, 3. This is only 3 J's. We split off a factor of I here in this definition because we like to see J be Hermitian, and it will make it so when we do that. Something similar happened in the case of translations, I hope you recall. And we split off a factor of H bar really just by convention, just because physicists like to see angular momentum have dimensions of H bar, and this is where this operator is going. It's going to turn out to be the angular momentum. And in the case, if we do this, it's just a simple substitution. And what we obtain for our infinitesimal U operator then looks like this, is that U of theta vector is equal to 1 minus I over H bar times theta vector dotted into J. And this is valid when theta is small. And it corresponds to R of theta in the same circumstances equal to identity plus theta vector dotted into script J, like so. All right. All right, now then. We want to find out what the U of theta is, the operator is, and we haven't actually done that, not even for infinitesimal rotations. But we have made progress because we've got the explicit theta dependence taken care of. The U of theta is a vast infinity of operators because theta vector can take on a continuum of values in 3-dimensional space of parameters, whereas J is only 3 specific operators. And so we see U of theta, at least when theta is small, can be written explicitly in terms of just those 3 operators. So this is actually a big improvement because now the problem of finding the rotation operators boils down to finding these J operators. We'll worry about that in a minute. But the theta dependence is now known. All right. Now, once we've got this, we now worry about what happens when theta is not small. And we'll go through the same procedure we went through earlier using limits, and we can work out a differential equation and find that, no, here's what we do. Theta is not small. What we do is we write u in axis angle form, like that, and we work out a differential equation for the angle theta. And if you do that, what you find is that it's minus I over h bar times n hat dotted into j times u of n hat comma theta. This is using this infinitesimal version up above in order to compute the derivative, exactly like I did a minute ago with the classical rotations. And so the solution is then this, is that u of n hat comma theta is equal to e to the minus I over h bar times n hat times theta. I'm going to write theta here times n hat dotted into j. And let me box that because this is the exponential version of our unitary operators. If you expand it out the lowest order, it becomes 1 minus I over h bar theta times n hat dot j plus higher order terms. And that's sometimes useful for small angles. Right. So you can see now that we've got an exponential version for the unitary rotation operators, and that in order to find out what they are explicitly as a function of n hat and theta, all we need to do is to know what j is. So let's talk about j. J has certain properties. The first one is that j, let's take the ith component of j, is Hermitian. So if I dagger j sub I, I get j sub I back again. This follows from the fact that the u operators are unitary, so that u dagger is equal to u inverse. It's exactly the same logic we used earlier to show that the momentum operator was Hermitian, or the k operator that was what we used in the way to defining momentum was a Hermitian operator. So I won't repeat the logic, but it's very, very simple logic. So these j operators are Hermitian. So we have a vector of Hermitian operators, which determine the rotation operators. By the way, it works the other way around too. If we knew the rotation operators, we could determine the j's, because they're given, is it still here? Can you see? Yes, they're given by taking derivatives. So knowledge of the j operators implies knowledge of the rotation operators and vice versa. All right. Now, however, these j operators have further properties. In particular, they have commutation relations. So let's talk about them. To do that, we'll go back to this mathematician's commutator that we talked about before. Let's look at this commutator again. Let's again think about small angles, theta 1, theta 2 here, and we called it phi for the c, if you'll recall. And now let's map each of these 5 classical rotations you see here, c and the 4 r's, into their corresponding unitary operators. So u of c is the left-hand side, and there's various ways of writing it. Given that c is an infinitesimal operation, a rotation, it was identity plus the phi vector dotted into script j like this, u of c must be equal to 1 minus I over h bar times the same phi vector dotted into the Roman j, which is the vector of Hermitian operators. That's from the left-hand side. But from the right-hand side, it must be equal to u of r1 times u of r2 times u of r1 inverse times u of r2 inverse, because of the fact that the mapping preserves the multiplication law. We move this up. And given that r1 and r2 have these various angles corresponding, so this is the same thing as u of theta 1 times u of theta 2 times u of theta 1 inverse, which is the same as a dagger if you want to put it that way, and u of theta 2 inverse, u of theta 2 dagger. As far as the u of theta 1 is concerned, we can write this out as a series. It becomes 1 minus I over h bar times theta 1 dotted into Roman j. Second order term is minus 1 over 2 h bar squared times theta 1 vector dotted into Roman j vector quantity squared plus dot dot dot. That's the first one. There are 3 more power series, which one can write out and multiply together, corresponding to the 4 factors like this. And I won't even bother to write out the details of it because I've sort of did that already. But, and I won't bother to do all the algebra, but it's straightforward to go through it. It's very similar to the algebra we went through with the classical rotations. And this turns into the following: 1 for the leading term, because they're all ones in here. The first order term vanishes, plus 0. And the second order term becomes -1 over h bar squared times a commutator of θ1 dotted into j vector with θ2 dotted into Roman j. All right. And now, is it still in the screen? That must be equal to the 1 minus I over h bar phi dotted into j. These correction terms have to be the same. This is second order corrections. So what we get is that minus I over h bar phi vector dotted into j is equal to -1 over h bar squared θ1 vector dotted into j commutator with θ2 vector dotted into j. But the left-hand side is also minus I over h bar times θ1 vector cross θ2 vector dotted into j. And now if I multiply through by h bar squared to bring this over to the other side, and if I write θ1 vector is equal to θ1 times n1 hat, similarly for θ2, then the factors θ1 and θ2 cancel, and I get the following formula: is n1 hat dotted into j1 commutator with n2 hat dotted into j2 is equal to IH bar times n1 hat crossed n2 hat dotted into j. And now these are arbitrary unit vectors, n1 and n2. If I made them x hat and y hat, for example, I get, I'm sorry, there's no subscripts in the j's. There's only one j. It's a vector of operators. n1 dotted into j, comma, n2 dotted into j. If I make n1 and n2, for example, x and y, then n1 cross n2 is z, and we get a commutator jx with jy is equal to IH bar jz, which should look familiar to you. And more generally, what we obtain is that ji, j sub j commutator is equal to IH bar epsilon ijk, j sub k. And thus, in this manner, we obtain commutation relation for the generators of rotations. That's what these J operators are, as generators of rotations. These are the quantum operators that represent rotations. We find a set of commutation relations, which are an obvious reflection of the commutation relations we had at the classical level, or the level of Euclidean geometry, of the script J matrices, somewhere in here, but you've seen it already. I can't find it now, but you know what it is. Can't find it because it's over here. Reflection of those commutation relations right there. Except for factors of I and H bar, which are essentially conventional, these are the same commutation relations. And the reason they satisfy the same commutation relations is because the U operators reproduce the group multiplication law of the classical rotations. And they do so for infinitesimal rotations, as they do for all rotations. And these J commutation relations come out of the commutators of infinitesimal rotations. Okay. So where this leaves us now is the following: is we still don't know what J is. In fact, you can't know what J is unless you know the specific physical system that you're talking about. However, just on the basis of the general properties of rotations, the fact that we have a representation of rotations, the J operators must be a vector of Hermitian operators that satisfy these commutation relations. And the rotation operators themselves, U of n hat comma theta in axis angle form, are given by E to the minus I over H bar times theta times n hat dotted into J. All right. And that's a summary of the first phase of this project of working out the unitary operators that implement rotations. This is as far as we can go, just on the basis of reproducing the group multiplication law of classical rotations. So let me pause here and ask if there's any questions about what we've done so far. I think if you remember what we did with translations, remember the translations, I had a translation of, let's call A as a displacement. This was equal to E to the minus I over H bar times A vector dotted into the momentum vector. So as we say, the momentum is a generator of translations, and here you can see that J here is the generator of rotations. We define, by the way, by definition, we say that J is the angular momentum of the system. The angular momentum, in effect, is defined as the generator of rotations. You know, in your typical first course in quantum mechanics, the angular momentum is defined as R cross P. Well, angular momentum of a particle moving in three-dimensional space is R cross P. There's nothing wrong with that. But there are other kinds of angular momenta, spin, and so on. There's also multi-particle systems. There's relativistic problems, and so on. The approach I'm taking here makes the definition of angular momentum as the generator of rotations, whatever that is on any system you have. And this is a more general approach, and it's more unifying and general approach, a better approach. All right. All right, if there's no questions about that, then I'm going to move on to the first application. First application is going to be that to spin systems, spin 1/2 systems, as a matter of fact. We had an example of this already when we were working on the Stern-Gerlach experiment. We found that the magnetic moment operator was given by a constant times the Pauli matrices. If you put it in the right basis, that's what you get. Let me remind you also that the Pauli matrices satisfy an algebra that sigma I sigma j is Kronecker delta ij plus I epsilon ijk sigma k. And I hope you know this well because it was the very first homework problem. It follows from this basic algebra that the commutator of two Pauli matrices, sigma I sigma j commutator, is twice I times epsilon ijk sigma k. Taking the commutator anti-symmetrizes and kills off the Kronecker delta and doubles the right-hand side. So anyway, these are the commutators of the Pauli matrices. So if we are going to look for rotation operators on our system of our silver atoms, here is a strategy we're going to use. We're going to look for a vector, 3-vector of Hermitian operators, J, that satisfy the angular momentum commutation relations. And if we find them, then we're going to put them into, exponentiate them with linear combinations with thetas and n-hats like this to obtain unitary operators, which will be candidates for rotations. Now, the reason I only call them candidates and not real rotations is because before you're done with this, you really need to check to make sure that the operators so defined satisfy the properties that you expect of rotations. It's not just enough just to do the math, and it has to make sense physically. So we'll do that. We'll do all of that. Maybe not all tonight, but that's where we're going to go. That's where we're going next. So the first step then is to find a vector of Hermitian operators that satisfy the angular momentum commutation relations. They look very similar to the commutation relations of the Pauli matrices. Just all you need to do is just scale it to get the H bar, the IH bar in and get rid of the 2. Turns out what you want to do is to define J is equal to H bar over 2 times sigma. So this then amounts to, the way we're presenting this amounts to a guess for the angular momentum operator for our system of silver atoms. And the question is it right? Well, if it is right, then we know what the rotation operators are, because it's going to be U of n hat comma theta is going to be equal to E to the minus I over H bar times theta times n hat dotted into J. That's general. But with this J up above, this turns into E to the minus I theta times n hat dotted into sigma, Pauli matrices, divided by 2. And again, by the very first homework exercise, you work this out. This is cosine of theta over 2 minus I n hat dot sigma times sine theta over 2. And just write this out. This becomes U of n hat comma theta. Let me box this because We have now got an explicit formula for the rotation operators for spin 1/2 systems. Okay. Now, this ought to also satisfy reasonable physical requirements on what would be expected of a rotation operator. Let's take, for example, the magnetic moment operator, which we know about from the Gedanken experiments we did. This is something by any reasonable definition should be considered a vector operator. I mean, it's a vector classically. Its expectation values is a vector and ought to transform as a vector, as a classical. The expectation value is a vector of C numbers and ought to transform the way that ordinary classical vectors transform under rotations. So therefore, let's do the following. Let's suppose I've got a state psi, and I map it into a new state psi prime by means of a rotation, which is equal to u of n hat comma theta acting on psi. Like so. Or let me just call it u psi for short, because I get tired of writing out the n hat theta. But anyway, we have one of these rotation operators. We apply it to psi, and let's call it psi prime. And let's consider the expectation value of the magnetic moment operator with respect to the rotated state. We can compare that to the expectation value of the magnetic moment operator compared to the unrotated state, which is over here. It just has no primes. What relation do we expect between them? Well, I think it's clear that the expectation value in the rotated state ought to be the rotated version of the expectation value in the unrotated state, where this r has the same axis and angle as this u, which is this u that I'm speaking of here. You can be explicit about that if you want. R of n hat theta in there, okay? On the other hand, the psi prime over here is equal to u psi, so the left-hand side can be written as psi, u dagger, mu, u, psi, like this, equals r on the right-hand side, multiplying that expectation value. Now, mu is proportional to sigma. Where did I write it down? Somewhere here I wrote it down. It's up here. So if we just cancel the mu naught, we can just replace the mu by sigmas here. We can also drop the psi's because psi is an arbitrary state. This ought to hold for all states. And if we do, we obtain a requirement that our u operator ought to satisfy, which is that u dagger sigma u ought to be equal to r times sigma. Let me box that. I haven't proven that this is true. All I've done is I've argued that on the basis of how the expectation values of vector operators ought to transform, this ought to be true as a part of the physical interpretation of that u should satisfy in order to be considered a rotation operator. Now, if this formula is not completely obvious, let me explain it. Sigma is a vector of operators. The operators act in the Hilbert space. So does the u. It acts in the Hilbert space also. Capital R is not a Hilbert space operator. It's just a 3x3 matrix. But the sigmas, again, are a vector of operators in the Hilbert space. So in order not to be confused about this, it might be better if I write it this way, is that if I conjugate one of the components of sigma by one of these rotation operators, what I get is a linear combination of the sigmas whose components are given by the classical matrix, classical rotation matrix. These two mean the same thing, and the upper box is just a shorthand notation for the lower box. So I hope that makes it clear what this is. All right, now the question is this true? Well, it is, and we can verify it by just doing some explicit calculations. If I just take the upper box, for example, and write this out, the u dagger is cosine of theta over 2 plus I n hat dot sigma times sine theta over 2. That takes care of the u dagger. The sigma I'll copy in the middle. The u is cosine theta over 2 minus I n hat dot sigma sine theta over 2. It's this thing here. And if you take this, you've now got products of identity matrices and Pauli matrices, including one term that's cubic in the Pauli matrices, that term times that term times that one. But we also have the algebra of the Pauli matrices here. And this algebraic relation allows you to take a quadratic polynomial in the sigmas and reduce it to a linear polynomial. By repeating that process, you can take any higher order polynomial, and cubic and others, and reduce them to linear polynomials by motivated application of this formula. And if you do that to this product of this thing here and just do the algebra, then here's what you find. You find cosine theta times sigma plus 1 minus cosine theta times n hat dotted into sigma plus n hat plus sine theta times n hat cross sigma. And I don't know if you remember, but this is this explicit form of the classical rotation and axis angle form multiplying sigma. So in other words, this formula is verified and is correct. So this then is an example of carrying out a program of explicitly determining the rotation operators, in this case for spin 1/2 system. We did it by guessing the angular momentum operator. There weren't very many choices here. Exponentiating to get candidates for rotations, and then checking that they satisfy the requirements we expect on physical grounds. These formulas that I've boxed here are important formulas. They're versions of what I call adjoint formulas. I spoke previously of an adjoint formula in the case of ordinary rotations, classical rotations, and this is a closely related formula here involving spinor rotations. They end up getting used quite a bit in applications, as we'll see. They'll occur in some homework problems as well. In any case, I'm just pointing out that these formulas that were derived here turn out to be quite useful in a larger context. That's a good beginning on spin rotations, and we're out of time, so let me stop here and ask if there's any questions. No questions.
If we have angular momentum from multiple sources, like both spin and orbital angular momentum or something like that, because the operator is linear, do those just like add in the exponent to give you your total J, or?
Yeah, that's a good question, and we'll get into that in more detail. What we really need to be talking about here is taking the tensor products of Hilbert spaces. This is where if you have a system that has subsets of degrees of freedom, for example, two particles, each particle has its own degrees of freedom, X, Y, and Z coordinates, for example, and we wish to construct a Hilbert space for the compound system. You do that by, in effect, multiplying Hilbert spaces. And it turns out that when you do that, the angular momentum operators add, more or less because they occur in the exponent. That's the idea. But in any case, we'll see. I'll go through it in somewhat more detail in a later lecture. But that indeed is coming up, and then you'll see that the total angular momentum is the sum of the angular momenta of the constituent subsystems.
Okay, cool. Thanks.
Okay, good. Any other questions? I want to say I've been getting such really good questions this semester. I'm really pleased about it. Sometimes some semesters I don't, and I don't know whether it's shyness or whatever, but it's really nice because I don't always remember all the things that I want to say, and these questions oftentimes bring up really important points. So keep up the good work, and if you haven't asked any questions yet, think about doing it, and if you don't be shy about doing it, please. Okay, I guess that's all for tonight. I'm going to stop screen share. And I'm going to stop recording.